Our next presenter is Dr. Federico Scafati. He's a structural engineer from Italy with ANAS, the Italian Agency for Roads and Highways, where he specializes in monitoring, safety assessment, and seismic retrofitting of bridges. He was formerly with Infra Engineering and Toto Holding, where he worked extensively on the isolation retrofit of existing bridges and the design of new isolated bridges in the L'Aquila region in the recovery after the 2009 earthquake. Federico's presentation is Seismic Isolation and Energy Dissipation of Bridges, State-of-the-Art Review and Applications in Italy. Federico.
Good morning to everyone, and thank you for your presentation. I want to add only that this work is in collaboration with ENEA, Italian agency, and is an overview of seismic isolation and energy dissipation in bridge located in our country. Everybody in this room know what seismic isolation and energy dissipation are. In the next slide, I will show you some notable application from all over the country regarding both new bridge and existing one, because in Italy we have a lot of bridge built between 1960 and 1980, and one of the main challenge for Italian bridge is to protect this structure against earthquake, because we are in one of the most seismic area of the entire Europe, and also because in the past Italy was not completely considered as a seismic country. So sometimes we have bridges that were designed without considering seismic action. But today, thanks to new anti-seismic device, we can use them to protect them, as we will see in the next slide. This is the Italian trend of the application of seismic isolation and energy dissipation in bridge. And from 1976, the first Italian application as in New Zealand, and up to today. As you can see from the green line, for the most of the time, the most used anti-seismic solution was energy dissipation system made of sliding devices and dampers. But in the recent years, thanks to new regulation that Italian government introduced to incentivize the use of a seismic isolation system, we have an improving of this application, and today the most used anti-seismic device in Italy are high damping rubber bearings, as we will see in the next slide. This is the seismic hazard map of our country. In violet and the red color, the most seismic area of the country. And for this presentation, I have chosen for you 7 case studies located in different positions of the country, not only in the seismic area, and obviously equipped with different anti-seismic solutions. The first 2 case studies are related to curved surface sliders. The other one, seismic isolators, high damping rubber bearing and lead rubber bearing. And finally, we have energy dissipation system. All the bridge are for example, the first one is San Giorgio, is a continuous deck, mixed steel concrete deck, supported by reinforced concrete piers and abutments, and the total length of the bridge is more than 1 kilometer. This bridge replaced the previous Polcevera bridge, designed and realized between 1963 and 1967, and partially collapsed on August 2018. The new bridge represents a unique example in the reconstruction of large infrastructure in our country, because time for design, construction, and test the new bridge was only 60 months. Also because this is a strategic infrastructure for our country, because connect the highway, the main highways and state roads in the north of Italy with the Genoa port, that is one of the most important ports in Italy. This is the longitudinal profile of the bridge. We have 19 spans, and below you can see the plan of the 42 anti-seismic devices. Look at the piers, because we have in this case the first and the last piers that are the lowest, and we will see in the next slide the anti-seismic solution adopted for this element. We have, in general, curved surface sliders devices, but this is not a total isolation because, for example, on abutments, we have multidirectional bearings located in the external position and a longitudinal guide located in the central one. This is a solution we can usually see in Italian bridge, especially in the recent years, because in this way we can optimize the structural response, and in particular we can optimize the joint behavior and costs. Multidirectional bearings are also located on the first and the last piers of the bridge, because we have seen these are the lowest and the most rigid element of the substructure, and for this reason we put multidirectional bearings to not transfer the forces from the deck to the substructure. The other piers are all equipped with curved surface sliders. In particular, we have two types of device depending on the vertical loads acting on them. On each pier, we have two devices, and one of them is equipped with fuse restraint because according to European standard, no friction shall be used to resist the effect of external horizontal loads in service conditions, for example, wind action. So for this reason, curved surface sliders can incorporate fuse restraint if necessary, and this is the solution that was adopted for San Giorgio Bridge. So for each pier, on each pier, we have one simple curved surface sliders, and the other one is equipped with these fuse restraint that are active in a static condition and also in a low seismic condition, but they break in a high seismic condition to allow the movements, the free movements of the deck. Another particularity of this device is that according to Eurocode, for this kind of isolator, no traction forces are permitted. And as you can see in the slide, this bridge is characterized by a particular geometry, because to satisfy the request of the architect Renzo Piano, who wanted a slender bridge, we have a wide deck, about 30 meters, with extremely narrow piers, less than 10 meters, and this made overturning checks of the deck severe, but they were satisfied. Finally, another particularity of the bridge is that maintenance and substitution and recentering function, because according to last Italian technical code specific for bridge, we have to ensure the maintenance, inspection and maintenance for bridge, also for new bridge during its lifetime. And in this case, vertical steel legs were placed next to each device to lift the deck in case of maintenance or substitution. Also to reposition the deck in case of not perfect recentering of the deck, for example, after an extraordinary event. And finally, to act as a buffer in case of displacement exceeding the design values. With this slide, I want to talk you with another bridge with curved surface sliders isolation system. But in this case, we have a shorter deck, less than 300 meters. And the particularity I want to highlight you is that in this case, we have piers with the same height, about 8.8 meters. So in this situation, we don't have the necessity to use different isolators or multidirectional bearings for the most rigid piers, because in this case, as you can see in this slide, we have the same isolators for each pier, while the same solution is adopted on abutment, because we have multidirectional bearings combined with unidirectional ones to optimize the joint behavior, allowing only longitudinal displacement. Another particularity is that inspection, the same aspect, inspection, maintenance. A pedestrian walkway was realized under the bridge to check the device and in general to check all the structural and not structural elements of the structure. With these two first case study, we have analyzed two bridges, both equipped with the curved surface sliders, and in both cases we have seen a partial isolation of the bridge because we don't have only isolators, but isolators are combined with multidirectional or unidirectional device. And in both cases, we have seen that great attention was given to inspection and maintenance according to the last Italian technical code regarding bridges. Now, I want to talk to you about other two case studies, seismic isolation system, but with rubber isolators, so high damping rubber bearing and the lead rubber bearing. We are in the most seismic areas of Italy for these two case studies. The first one is the Genzano Bridge. This is a new bridge, totally rebuilt after the 2009 L'Aquila earthquake, with two independent carriageway, less than 150 meters long for both the carriageway. And we have 4 span for the left carriageway and 10 anti-seismic device. The right one is longer, 5 span with 12 anti-seismic device. The anti-seismic solution in this case is simple because the device is the same, and the main characteristics are shown in the table, but I want to highlight you in particular 2 things. According to Italian technical code, for this kind of device, we can use dynamic linear analysis, and this is the reason why we have seen in the first slide that today are the most used device, the most used isolation system in Italy, also because they are good for different type of structure. And the other one is that this kind of device are able to support also traction load, differently from curved surface slide that we have seen before. This is another case study equipped with a lead rubber bearing. Retiro Bridge is in the south of Italy. It's part of more complex infrastructure that made also ramps and that connect the highway, so the main bridge, to the local roads. And this is an existing bridge because the seismic retrofit project consisted in the substitution, the replacement of the previous pre-stressed reinforced concrete deck with a new steel one. Also, the piers were reinforced, and the constraint system between the substructure and the superstructure, in this case, were lead rubber bearing. This is the plan of the infrastructure, and I have highlighted for you in blue color the bridge we are analyzing. Is characterized by 2 independent carriageway, and this is the plan of the 88 devices. We have in this case, to optimize the structural response, 6 types of different lead rubber bearings. But also in this case, we have used dynamic linear analysis because the behavior of the device is linear. And also in this case, we have the maximum traction force of more than 1,000 kilonewton. So with these other 2 case studies, we have seen lead rubber bearings and high damper rubber bearing devices. And we have seen that they are useful because they can support tension stress, and also because dynamic linear analysis could be performed for this case. And in both cases, we have analyzed a total isolation of the bridge, but this is not the only possible solution, because obviously this kind of device can be used also combined with other devices. And this is the example of the Filomena degli Castelli Bridge. It is located along the coast of Italy, so not a high seismic area. It is a semi-fan cable-stayed bridge with a total length of 188 meters, and a central span of 103 meters. The plan of the 10 anti-seismic device is shown in the picture. As you can see, in this case, we have multidirectional bearings under the main beams of the deck, and the lead rubber bearings are located only in the central position and only in correspondence of the pylons of the bridge, as you can see on the picture on the left. Otherwise, on abutments, we have that multidirectional bearings have to be able to support traction load, and this is the case because we have a maximum traction force of 1,000 kilonewtons. So in this case, the traction force is not supported by lead or lead rubber bearing or high damping rubber bearing, but directly thanks to the multidirectional, this particular multidirectional device. And another particularity of this project is that we have also not a unique device in the central position, but we have the composition of 4 lead rubber bearings put together with steel plates with equivalent viscous damping of 25% to improve the total equivalent horizontal stiffness of the structure that obviously is the sum of the single equivalent horizontal stiffness. Now I want to close this presentation with the last 2 case studies because we have talking only about seismic isolation system with a total or partial isolation of the bridge, but now I want to talk to you about energy dissipation. The first one is another example of semi-fan cable stayed bridge, but in this case we have a more complex bridge because the total length in this case is 440 meters. The maximum pier height is 92 meters, and this bridge is located in one of the most seismic hazard area of Italy, near the Strait of Messina. This is a new bridge, part of the modernization work that involved the A3 Salerno-Reggio Calabria highway in the south of Italy and is characterized by 2 independent carriageways. This is the plan of one of them. We can see 8 anti-seismic devices in this case. We have unidirectional bearings placed under the pylons up to piers, okay, P1 and P2, and we have in this case a double elastic restraint, we will see in the photo in the next slide, located on abutments both in a longitudinal and in a transversal direction. In this case, on abutment, we don't have multidirectional bearings or rubber bearings able to support the tension forces, also because in this case, the maximum traction forces is 5,050 kilonewton a lot. And in this case, the solution is to put these steel connecting rods on abutment that connect in vertical direction the deck on the abutment. In longitudinal direction, we have seen the previous slide, we have the elastic restraint that connect the deck, but only on the SB abutment, while the other abutment is free to movement, and in fact, the maximum displacement is 250 millimeters. Obviously, in the central position, the unidirectional bearings are characterized by increasing movements from P2, 50 millimeters, to P1, 150 millimeters. Now, I want to talk I want to show you the last case study, is another bridge part of the seismic retrofitting project that involves the 25 between viaduct and bridge located near L'Aquila along the A24 highway that connects L'Aquila to Rome. So this bridge, after the 2009 earthquake, was retrofitted, and also in this case, the retrofitting consists in the replacement of the previous pre-stressed reinforced concrete deck the reinforcement of the existing piers, and the use of energy dissipation system in this case. The new deck, differently from Favazzina bridge we have seen before, is free to movement because we don't have a rigid connection to abutments, but in longitudinal direction we have a longitudinal viscous damper that allow, as we will see in the next slide, movements in statics and also in dynamic condition. Another particularity is that the two adjacent carriageway were connected to optimize the structural response of the entire bridge. This is the longitudinal profile of each carriageway, and below you can see the plan of the 50 anti-seismic device. Pay attention on the central pier, the P3 central pier, the highest, 51 meter, and the P5 pier, the lowest, with 15 meters. So a big difference. And for this reason, we will see in the next slide, we have different solutions adopted for each pier. But start with the abutments. On abutments, we have 8 longitudinal viscous dampers and 4 transversal ones to control the horizontal displacement of the deck, while we have also 8 multidirectional bearings to support vertical loads. Transversal viscous dampers are also located on each pier, while in longitudinal direction we have a different behavior because we have on P1, P2, and P4 spherical bearings combined with shock transmitters. On the central and highest pier, we have only unidirectional bearings that allow transversal movements because P3 is the central pier. The deck is free to movement on abutments, so it's the fixed point when you have thermal expansion and construction of the deck. For this reason, on P3 we have transversal unidirectional transversal bearings, while do you remember the P5 pier, the lowest and the most rigid pier of the bridge, is equipped also in this case, as in San Giorgio Bridge, with multidirectional bearing because we have existing piers. We don't want to overload it in seismic condition. For this reason, we put multidirectional bearing. In general, this is a complex energy dissipation system, but we can summarize in the next 2 slides because it is designed to perform differently in static and dynamic condition. This is the static condition. As you can see with the green color, the free movements, and the blue color, not permitted movements in static conditions. So in longitudinal direction, movements are permitted except on the central pier, the fixed one. While in transversal direction, all the viscous dampers blocked the movements. In seismic condition, we have that all the longitudinal and viscous dampers can dissipate the input energy in the violet color, while in longitudinal direction, shock transmitter block the movements, so are not permitted on all piers due to shock transmitter and also unidirectional transversal bearings. So all the piers in longitudinal direction are blocked, except the most rigid one, the P5 pier, because we have multidirectional bearings. So in this case, the piers and the deck up to the piers is free to move. Sant'Onofrio Bridge is a candidate to Assisi Awards, so if you want more information about this complex energy dissipation system, you can visit the website, obviously. And the last 2 slides are to say thanks to all those who have provided data, articles, information about the case studies used in this presentation, and in the corresponding paper you can see for this conference. And obviously I want to say thanks to all of you for your kind attention.